مرحبا طلاب، كيفكم؟ اليوم راح أبدي بشابتر 6. chapter 6 it's about electrical system, okay? Which at the beginning I think it will be easy for you as we taken this before, but it's okay, we have to start from the beginning. So if I have this circuit, which is, we see it a lot, it's RLC circuit, and we are looking for the model. The model could be a differential equation, and then could be it's in Laplace, it doesn't matter as long as it's a linear system. So in this model we say V of t, which is the input, equal L di by dt plus Ri plus 1 over C integral of I dt. This is C, of course, okay? And I can go into two methods or two approaches. If I want the output Vc over the voltage, the transfer function, then I can go into one direction, or if I want the current to be my output over the V, which will be the transfer function. So the transfer function could be Vc over I over V of t, or I over V of t, or maybe I take the voltage across this or the voltage across this, whichever the element you choose as you take the output, the voltage as the output. Now you remember that I equal dq by dt, which is q is the charge and q is the charge. Integrate that di by dt equal d square q by dt. I can substitute those in the original equation. The target is to get rid of this integration. Okay, get rid of this integration. Now v of t equal, when I substitute here, we said I equal di by dt, and then di by dt equal L d square q of t, by dt square plus R dq by dt plus 1 over C, and di by I equal dq by dt. So if I integrate, so I'll get the integral of I equal q of t. So it will be this, will be 1 over C q of t. This is one equation. Or I can go into, if I want the output to be Vc, then I know Vc equal 1 over C the integral of I dt, or I equal to CVC. Then Vc equal 1 over C q of t if I want to substitute in that equation. I don't want to go to the original one, okay? Then q equals CVC. Now if we substitute in here, in that one, in the C, I'll get this equation, which is V of t equal to LC d square Vc by dt square plus RC dVc by dt plus Vc of t. Here we chosen the output to be Vc, right? Now take the Laplace transform. We say V of s equal LC s square Vc plus RC s Vc plus Vc of s, or take Vc out of all this part, and we get LC s square plus RCS plus 1 equal times Vc of s equal V of s. Or if we divide by LC to make the coefficient of the s square equal to 1, then we'll have Vc of s over V of s equal 1 over LC over s square plus R over L plus 1 over LC. This is the transfer function. You know, I can put it in a block diagram like that, if you like. This is the G of S. The input is V, the output is Vc, and this is RLC circuit, something like that. The easier way to deal with this circuit is put it into Laplace transform from the beginning. So L will be Ls, R will be the same, capacitor will be 1 over Cs, this is Vc of s, the current will be I of s, the input will be V of s. So I can say V of s equal the voltage across L, VL, plus the voltage of R plus Vc. So V of s, it will be Ls. Now imagine this as if it is resistive circuit. So we'll say that the current IS equal the voltage divided by this added up altogether, as if this is R1, R2, R3. Okay, imagine this as if it's resistive. Once you put it into Laplace, which is the frequency domain, then the analysis will be much easier, and the current will be V over summing of all these. So I'll say V of S will equal LS plus RI plus 1 over CS VI of S. Okay, so transfer function, if I want to be I over V, it will be 1 over LS plus R plus 1 over CS, and multiply both denominator and numerator by CS. Then you will get CS over LC S square plus RCS and plus 1. Okay. Now, if you want to find VC, then we know that VC equal, we said we imagine this circuit as a resistor, so VC equal the current which is flowing into this times the impedance. We don't say resistor, we say impedance, but we treat it as if it is a resistor. So it will be 1 over CS times the current. So VC of S equal 1 over CS times I. ينتج I of S equal C S VC of S. Then we substitute V of S equal this equation, this one, I'll go back to it. I called it VB. So I'll substitute for VC of S equal 1 over CS times I, and I equal to C VC of S. So we will say that V of S equal LS plus R plus 1 over CS, CS VC of S, and I can get VC of S over V of S, which is the output over the input, and I'll get this, and it will be equal to 1 over LC S square plus R over LS plus 1 over LC. Okay. I hope it's clear. Okay. Now, if we put it as a transfer function, if you like, so this is the input here in this situation, V of S, the output is VC of S, and this is the transfer function. The transfer function in this case is that one, okay? Now, if we take a circuit with two meshes, we set I1, I2, and R1, R2, L, and it's a capacitor here, and maybe we choose I2 to be the output. So immediately put it into Laplace. So I say V of S, this is R1, this is LS, this is R2, this is 1 over CS, okay? And the output is VC. If you want the output to be VC, I will take the output to be I2 now, okay? Now we write the meshes. If we want me to go back into this, we say that for this one, it's equal V of S. No, this one. If we go to this one, then I'll go into the equation. I just show you. I will remind you actually, because I hope these are easy for you. We say that V of S here in the Y equal R1 I1, R1 plus LS I1 minus LS times I2. Okay, if I go to this one, of course I can move this after the equality. And this one I say minus I1 LS I1 plus LS plus R2 plus 1 over CS times I2 equal to 0. Okay, and these equations are stored on the next page. So R1 plus LS I1 minus LS I2 equal to V of S. This is mesh 1. And mesh 2 minus LS I1 plus LS plus R2 plus 1 over CS I2 equal to 0. So we have equation 1 and equation 2. We can use, you remember that Cramer rule, and we want the transfer function to be I2 over V of S. Then using Cramer rule, we put I2, it will be, this is delta in the denominator. You remember delta, it's the determinant of the transfer function. And here we'll take we want I2, so I2 in column 2, I'll take away I'll show you in delta. This is the delta. The delta is the determinant. When I put this, like these vertical lines, it means this is a determinant. The delta is the determinant of this matrix, which is R1 plus LS minus LS minus LS, LS plus R2 plus 1 over C of S, which is from this equation, okay? So the matrix, let's call it the A matrix, R1 plus LS minus LS, and then the next row is minus LS, LS plus R2 plus 1 over CS. So in this matrix, this one, if I want I2, I'll take this away, and I'll put the B metric, which is V of S and the 0, and this is the delta, which is the determinant of this, okay? And this equal to here, if we find this the determinant, this time this will be 0, minus, and there is a minus, so it will be plus LS times V of S. Of course, this should be big. So this will be LS V of S over delta. What's delta? It's equal this times this, minus LS square, and this minus by minus plus, and we have a minus, so it will be minus LS square. So the delta will be here, R1 plus LS times this, minus L square S square. So I2 over V of S equal LS over this denominator. I didn't simplify it because it's, no, yeah, I think you can manage that. Of course, when we talk about system with connected together like meshes or things like this, we talk about loading effect. What's loading effect? We'll see that in the next topic. You remember in control system that if we have G1, G2, they are connected, we say in cascade, then the transfer function, which is x3 over x1, it will be G1 times G2. This happen and this is true when G2 has no effect on G1. Okay, no effect on G1. That means this is a separate identity and this is a separate identity. Each one has its own transfer function without the effect of this on this one. If there is effect from this on this one, then you have to take it into consideration. And you know that this one is x2 over x1 and this one x3 over x2. So the total will be G1, G2. This is what we call cascade. So when we put it like that, if you remember taking it in other subject, like if you take in control, I'm saying, otherwise it's like that, it's nothing big. So if you have two transfer function in cascade, then the total transfer function equal G1, G2, provided that there is no loading from this onto this one. I'll remind you of something which is similar to this. You remember in control, and we used to connect a load on the motor, and when we calculate the parameters of the motor, we calculate the effect of this loading on the parameters of the motor, like the moment of inertia and the damping. So we add them up together. We said that the moment of inertia of the whole system, the motor and the load is added together, and the damping as well. So this is called loading. واضح? In circuit, loading is treated by buffering. How if I have a circuit, I'll show you the next circuit. Let's say I have this circuit. Let's say I didn't put an isolating amplifier. Okay? If I don't put isolating amplifier, then I have to calculate the transfer function A out ila A in the same way we did with the two meshes we treated. Let's say that this is not disconnecting, and our connection, it will be, let's say it's like that before we add the amplifier. So if we don't have amplifier, we will have this one and this one and this. This is A out and this this is 1 over C1S, this is R1, this is R2, this is 1 over C2 في S, and this is En. So if I want to calculate the output, if it's Laplace, then this will be E out, this will be En in Laplace, this will be I1, whatever. So you have to apply either meshes or you apply node analysis. You will see the effect of this part over this part. So I cannot say that the transfer function for this, it will be G1 due to this and G2 due to this. Okay, I cannot say that. Why? Because this has a refraction on that one, has an effect on that one. What do? They do is that way. They put on separation as isolating, they call it isolating amplifier or buffering with gain K. You know that the amplifier has an infinite input impedance, so it will not, this will not affect on that. So in that way, I can get rid of the loading from one circuit to another. In this way, I can say if this, if these values are equal this, I can say the transfer function is that part squared. Okay? But now they are different, so now I can put that the transfer function equal the transfer function due to this one, I call it G1, and the transfer function due to this, which is G2, and I put this in the middle with a gain, and the gain you can choose it. Okay? So to find the transfer function of such a system, okay, then put it in Laplace. So this will be R1, this will be 1 over C1S, and this will be R2, this will be R1 over C2 Vs. Let's call this E out, let's call this E1, let's call this E2. So if we want E out over E1, it will be 1 over C2S over R2 plus 1 over C2S, and this equal to G2. So I'll call this one G2. So E out إلى this is sorry, this is E1, not En. Okay, so that will be E out over E1, not forget about this. E out over E1 equal 1 over R2 C2S plus 1. I found the transfer function of that part. Now I found the transfer function of this part. It will be 1 over C1S over this one, okay? I'm taking them separately because it's I have this amplifier serving as I can do that. If I don't have the amplifier, I do it the way I did the two circuit we have. We made meshes and we applied the Cramer rule, right? But if I do this, I can find the transfer function of each side separately. So this one, E2 over En, it will be 1 over C1S al R1 plus 1 over C1S, and it's equal to 1 over R1 C1S plus 1, and I'll call it G1. Then this system, I can put it in that way. En, it went into G1, which is that one. Then this is the gain K, that one. And then I have E1, which is this. Then I have, sorry, this is G2. G2, okay? I'll put it here, G2. So that the transfer function E out إلى N, it will be this time this time this. The method of okay, I'll repeat this, but this one, it wasn't clear. So now I found the transfer function, this one, E out over E1, and the transfer function E2 over En, and now I can put it as cascaded. So I put this one, it will be G1, and this one, it will be G2, and in between, because I have this isolating amplifier, so I put it as gain K. I don't ignore it, it's a gain K. So now I can say that the transfer function E out over En equal G1 times K times G2, like that one, okay? So if I isolate, then I can do this separately. If I don't isolate, I have to solve it like the example with the two circuits, with the two meshes, and I solve it by Cramer rule, and I find whichever transfer function I want, the output or the I1 over, I2 over the input, and so on. Now, you remember the electromechanical system. I'll go back into electrical later when I give you some about the amplifiers and type of amplifiers, and the ones that I think that you can manage, okay? Not all amplifiers, because it's quite a deep subject. So to find the transfer function, this the DC motor is called electromechanical system because it consists of an electrical part and a mechanical part. So, and we take this, which is armature control type. We have field controlled and armature controlled. Armature controlled is more easy to control, and we can approximate it as a second order system, and then it's manageable. So this system to show you, I want to remind you or show you how I get to this schematic diagram and how I get to this block diagram. If I get the block diagram, then I can find the transfer function or the differential equation that relate every variable in this system. To do this, so I have to go back into a bit into the model of DC motor just to refresh your memory. So I'll do this in the next video. So see you. Bye.